Okay, so like I said, we're going to be talking about the history of an atom. And so atoms cannot be directly seen. So this means that with all of our tools and stuff, we cannot see atoms. What this means is that all known information or all known info is based off of inferences from experimental observations. That means the basis of so much of chemistry has never actually been seen. Experimental. That's one of my little shorthands there. All right. So that means as technology improves, so does our concept of what an atom is. So this is the beautiful relationship between technology and science. It's very intimate and it's very cyclic. So as technology improves, science improves. As science improves, technology improves. As technology improves, science improves, etc. So currently, our model that we use of the atom today is developed through contributions from many key people. So it's not just one person, but it's contributions of a lot of different scientists. That is our basis of the model of the atom we have today. So we're going to talk about the upbringing of atomic theory, starting with Democritus and Leucippus. I don't know. All right, so how they believe the atom, how they described it, is an indestructible thing or smallest piece of substance. So this is all the way like 500, 400 BC. No other theory was really thrown out there or accepted or talked about until John Dalton came by over 2,000 years later, okay? And so his model, he said that it's the smallest piece of matter and that atoms of the same element have the same atomic mass but different, or DIFS, masses than other elements. So what I mean by this is any atom of one element type, so one atom of hydrogen compared to another atom of hydrogen have the same mass, but if you compare an atom of hydrogen to that of oxygen, they'll have different masses. And so what you can think of his model as just a solid sphere. This is his model. How he arrived at that is strictly from a thought process. So by thought, what did he think? If you took something, cut in half, over and over, until it cannot be cut anymore. That's what an atom is. So if you took a grain of sand and you cut that, then you took another half, cut that in a quarter, take the quarter, cut it an eighth, and keep cutting so you can't cut anymore. That's what he believed an atom was. Now, the way that he arrived at this, like contributed to his model, besides just the thought process, is using a battery. So used electricity to split water, H2O, into hydrogen or H2 and oxygen, O2 gases. And O2 gas weighed 8 times as much. All right. So Dalton, his theory, developed from a thought process, is that we have the solid sphere and that atoms of the same element weigh the same. If you're comparing atoms of different elements, they'll have different masses. All right. About 90 years later, I thought someone was just throwing up in here. That was very scary. Bless you. Oh my goodness. All right, so not much time has passed. We have Johnson, or sorry, not Johnson, J.J. Thomson and the Crookes tube. So Chance and I just spent so much time looking through the Crookes tube, we couldn't find it. So I have a demo for you guys, but I don't know where it is. So I'm like really sad because it's really cool. So when I find that, I'll show you guys next class period. But anyway, it's not the same. It's not the same. But I'll explain the model. Anyway, so we have what's called the plum pudding model. I'm assuming, has anyone had plum pudding? No. Okay, so makes sense since this is a late 1800s term. I'm gonna call this the chocolate chip cookie model. So I'm just gonna say choc chip cookie, because you guys have eaten those, right? Or at least know what they are. All right, so what the plum pudding or chocolate chip cookie model is that you have a sphere of diffuse positive, which I write as plus in parentheses, charge in which negative charge electrons are embedded. One sec, I need to plug this in. So what does it mean? I want you to think of a chocolate chip cookie. So the dough, the lighter brown part of the chocolate chip cookie, think of that whole area being like the positive charge. Then each chocolate chip would be like an electron of the atom. So this is a visual representation of this positive area with negative electrons embedded in it. Plum pudding is like think of it like yogurt with raisins in it. So it's the same idea of like a chocolate chip cookie, except just from the early or late 1800s. Yes.
Like, is the positive charge bubble solid, or is it just like an area in which
Think of one big sphere that anywhere where those little electrons aren't, that's positive. So it'd be like a balloon filled with air. Everything inside the balloon is positive, except maybe you put some beads in there that would be electrons. Yes.
What is this describing?
This is describing atomic theory. Yes, what an atom looks like. This is what they thought. I'm going through the progression of how we got to atomic theory today, which is a solid sphere. Now we're graduating to a positive sphere with negative electrons embedded. Any other questions? All right, so how did Thomson arrived at this. So how he arrived was using what's called the Crookes tube. So he used the Crookes tube. And discovered electrons. So Thomson discovered the electron. So because the negative particles had to come from somewhere, atoms must have smaller pieces. I'm so mad I don't have the thing for you guys right now. All right, so far we have graduated from a solid sphere, a small, solid, indestructible sphere, to now we have this sphere that has positive and a negative parts. And now we're going to take it one step further and talk about Rutherford's model with the alpha particle. So his model is that there's a small, dense, positive nucleus with electrons orbiting outside at a distance. Yes, I use an @ sign for @. You guys can use that too. So his model looks like this figure I have here, where we have a small, dense, positive nucleus and electrons orbiting outside the nucleus at a distance. So the key here, I have to emphasize on here, is that most of the atom is empty space. And so how he arrived at his model is with the gold foil experiment. So what he did is, if you look at this picture below, we're looking at this one right here. How he had this set up is he had an alpha particle beam. That's this red beam here. So it's shooting alpha particles, which are positively charged. So think of just a beam of positively charged things, and he's putting it at a pure sheet of foil of gold. Everywhere around the sheet of gold is a detector screen, so it can tell where those particles hit after making contact with the foil. Now, looking at part B here, according to the detector, most just went straight through the foil. So meaning most just went straight through to the other side. But there were a few that were bounced back or deflected, meaning they had to find something else positive in there that would change its direction. So this is how we came up with the idea that we must have a small, dense, positive nucleus that some of the alpha particles deflected off of, but most of the atom's empty space because majority of the alpha particles went straight through it. So most, I'm going to write alpha or positive particles passed through foil. A few bounced at an angle, and very few straight back. So again, I'm just going to make a note here that this particle beam the alpha particle emitter is that the alpha particle is a positive charge. How he arrived is that he observed light given off by several heated elements. And I don't know if you guys know this, but every single element gives off its own color.
This is stressful.
So I'm gonna make this note here that different elements have different colors. This is gonna be our experiment on Wednesday. Exactly. So have you guys seen fireworks before?
Yeah.
The color is based on the elements that they package inside of them.
Which ones are?
Yeah. All right. So what he drew from this is that different light spectrums. So these are called light spectrums. This is a light spectrum. And we'll talk about what that is. So different light spectrums mean likely differing element energy levels. With a specific amount, I abbreviate AMT, of energy associated with them. So pretty much what happens is you guys have seen, if you put light through a prism, it creates a rainbow, correct? That's because white light is actually made up of all sorts of wavelengths. So if you take the light of heating an element, so for example, hydrogen gas, put it through a prism, it breaks it down into those wavelengths as well. So that is what is happening in this picture. It's breaking down the gas's colors into what wavelengths make it up, because each color has a wavelength associated with. We see just one color, hydrogen might burn purple, but really we can break it down into different energy levels that make it up. So we're going to get into that a little bit more here, talking about spectroscopy, which is the idea of kind of like what a prism does, but us analytical chemists have made it that much farther and is the tool that we use all the time. So when we study how these electrons move from their different energy levels, it's called spectroscopy. Yeah. That has to do with the energy level. So any color we see is our eyes absorbing the energy from those materials. It's so pretty much why we see different colors of light is from the release of energy back. So the light that we see is produced from electrical current, which produces energy that gets put into our clothes, which then vibrates the electrons in our clothing. And then that releases the energy back out as photons of light is what we pick up in our eyes and see. It's pretty cool, but it's crazy. Yeah. Anyway, we'll get into it. We'll get into it this next part here. So we have this thing called grating. This grating acts like mini prisms. So there's just a bunch of little prisms waiting to break apart one beam of light. So like I said, white light is made up of all the colors of a rainbow. That's why you see a rainbow when you put white light through a prism. And so it's actually, this is a key, release. It's the release of energy that causes different colors. Or that color causes colors. We'll leave it at that. So this is where we're going to break down this next little chart here. Okay, we have an atom. where I'm gonna use this color and pretend that I have some source of energy. So I'm gonna use this lightning bolt as energy. Now, what we're gonna use for lab is a flame. We're gonna light our atoms on fire. And so we're adding energy into our atomic system. What happens is that we actually put energy towards one of our electrons and excite it to a higher energy level. But so if you guys are at a concert, you're all hyped up, you're excited from the energy you're getting, right? What happens when the concert's over? You crash, right? You can't stay in the excited state forever. That's how these electrons feel. So at a certain point, which happens a lot quicker than us going to a concert and crashing, they come back down. And as they go back down to what's their ground state, where they're grounded, that's where they like to hang out, they release what's called a photon. This photon has a certain wavelength depending on the amount of energy it's releasing. Therefore, corresponds to a certain color. So the energy difference from an electron jumping from ground at 0 to level 2, that's going to produce a higher energy, smaller wavelength, because they're inverse, and one color, versus if it only jumps one level, lower energy, larger wavelength, different color, okay? So these wavelengths, that's lambda, which equals wavelength. So those are the wavelength. And so notice the wavelengths for the lower energy is bigger, higher energy is smaller. Yes. So this is, okay, so the photon only comes from going to a back down to a lower energy level. That's the only time you could, because the energy has to go somewhere. So you are not causing a photon increasing outwards, only when you lose that energy back out into the system, okay? Good question, yes. Correct, and it's inverse. So the higher the energy, the smaller the wavelength. Hello. I'm gonna wrap up one thought here. Yeah, go ahead.
Does the photon land? Should there be some way
No. I mean, if we don't even really say an electron has mass and a photon's even less than that. So a good question. Any other questions before we finish up our last thoughts here? Okay, don't worry, we'll play a lot with this during lab. So you guys will have a pre-lab, I'll get that posted. We'll talk about it a lot. It's not the most straightforward thing. So this picture is showing the progression of atomic theory, right? So we start with a solid state, then we add positive and negatives, then we say actually the electrons orbit, and then we take one step further, actually they orbit at energy levels. Then the last one we have is today's current model, which is the quantum mechanic model. So that's electrons orbiting, travel in a wave-like pattern. And then we also have to have this idea that the electron's motion is affected by mass